Hello everyone, thanks for your attendance. And today's my topic is the broadening the view synthesis of dynamic scenes from the constrained monocular videos. And so firstly is the challenge identification. So we know that there's already extensive research on the static object reconstruction. So where we can simply work around an object and capture the image from the many angles. But for the dynamic entities like the wild animals, performer, on the stage or the sports game viewed from the fixed seat. So moving freely around the subject is not possible, or at least not easily. So we call this is the camera constraint. So we it's effectively a small data set, the small data problem. So shooting from a single direction give us no information about unseen side views. So you can see the problem here, just all of the metal, this kind of the NeRF type the metal render the sharp readout from the primary viewpoint, but as soon as rendering cameras deviated from the original capture angles, the output rapidly degraded and blurred shapes or fractured geometric or artifacts anywhere. And this things has also happened on the Gaussian splatting, but I think I didn't put the videos here, but we can show the readout later. Uh, and this is an inherent limitation of the monocular training. So the model has never seen any supervision signal outside the primary view. So to address this, we propose our method, the expanded dynamic nerve. So here's the overall architecture. The expanded nerve just have the two main components. The first is the backbone dynamic nerve. As a reminder, the nerve just take the 3 points and viewing direction and output the color and volume density. So that is the C and sigma you see in the figure. So our backbone just use the two intertwined networks. So one of for the static background, use the 5B in the figure, and one of the dynamic foreground, use the 5F in the figure. This two branch has the asymmetric input by design because the 5B just takes all n frames together with no time conditioning, so it can only model the content that is consistent across time. And 5F takes the time step t to as the additional input, so it is only the branch that can represent the time variant content. So use this way to separate the foreground and the background. Just do the decomposition for free without any manual segmentations mask. And after we segment that, just the second part is the novel view feature optimization branch. So this branch used the Gaussian splattings prior to generate the pseudo ground truths for the arbitrary viewpoints on every frame. So we then update the color and density feature through the dedicated novel view losses, enhancing the representation across many perspectives. And we choose the Gaussian splatting for the priority because it strikes the right balance between the training efficiency and the rendering quality, and perfect for the generating the high fidelity pseudo GT without dominating the total training cost. And and this part might be a little bit outdated, but just this is the reason why we choose the NeRF rather than the Gaussian splatting as the rendering backbones. Here's the comparison between the instant NGP and 3GS. Just from primary view, both like defines, the sky is uniform and the scene is consistent. But on the side view, the Gaussian splattings just introduce the artifact. The sky is mistakenly reconstructed as a nearby structure and blocking distance, mountains, and bushes. And the instant NGP just preserve the skies as expected. So I think this is kind of the limitation of the Gaussian splatting handling the object without clear geometric boundaries or at infinity depths. So at least when we start this project, so we use the Gaussian splatting only as the prior generator for the foreground, and while the NeRF remains the actual rendering backbones. But I think our method can be rendering background agnostic, so we can also switch to purely Gaussian splatting work. So if showing the better result. And now is the go into the methods part. So through the previous experiments, so we observed that the foreground object degraded much faster than the background when the viewpoint rotated. This due to the affine distortion, just the objects closer to the camera undergo the larger apparent motion than the distance ones. So we prioritize the foreground optimization. The residue, the background blur, is later handled by the super resolution loss. So for each input frames, we reconstruct the 3D Gaussian mesh for the foreground object using the some work like the free splatter or the dream Gaussian, this kind of the work around that object. We define a dome sampling space. So the primary recording view is shown as the red camera. The deviated novel viewpoints, showing the black, are sampled by the rotating around the object azimuth from the minus 45 degree to the 45 degrees in 5 steps at 3 elevation levels at 0, 15, and 30. So the Gaussian mesh and the dome together provide the pseudo ground truth from all these angles. And the remaining question is how to fit these dome cameras into the NeRF. So the Gaussian's prior lives in its own coordinate system, so which does not align with our with the NeRF world frame. So to use the dome cameras as supervision, we first need to compute the rigid alignment metric. Is the t equals the primary camera pose in NeRF coordinates times the inverse of the primary camera pose in the Gaussian prior coordinates. So we then transform every dome cameras through T so that all nova views land in the NeRF frames. So for each transformed nova view, we cast arrays, query the foreground network phi f, and compute the normal view loss. And it has the two components. I think that is in the this here is one is for the sigmas for the density, and one is for the color. And the two this kind of two loss. And this is the loss composition. Our method is trained with the 4 complementary losses. The first one is the reconstruction loss. There's the classical NeRF photometric loss on the real primary view, and one is the continuous. The loss is the temporal smoothness on the foreground density for the stable motion. And one is the super resolution loss. I will cover on the next slides. And one is nova view loss. Just we just discussed. So the total objective is simply the sum of these 4 terms. And one important detail is the novel view loss is defrauded until after the warm-up phase. Just applying it from the iteration 0 causes exploding gradients because the primary view reconstruction itself isn't yet stable. And the NeRF rendering often just looks slightly blurred because the per ray sampling budget is limited. And after the rotating camera, so even if the background is it's quite stable after the rotating, but it still have some influence. So to recover the crisp texture, so we attach the super resolution loss inspired by the real ESR again and the NeRF SR. So as shown in the diagram, the rendered low resolution patch, a pixelated thumbnail on the left and flows through the frozen real ESR again model. So it's upscaled output and together with the high resolution reference. So it's then compared at two levels. The one is the pixel-wise L1 loss in the golden node and multi-layer VGG perceptual loss in the blue node. So both contribute to the final SR loss budget on the right. So one important thing is that the SR loss alone without the geometric supervision actually will amplify the artifact. So the SR network only adds the value once the novel view loss has already stabilized the foreground geometry. And this also will show in the ablation study later. And to demonstrate the model and provide the ground truth needed for the quantitative evaluation. So we introduced the new dataset, the synthetic dynamic multi-view dataset, SynDM. We leverage the high fidelity, the open world game GTA 5 as the source platform. By default, the GTA 5 only supports the single active viewpoint port, which make the capturing the synchronized view multi-view dynamic scenes very challenging. But of course, just no more challenging than the equivalent the captured setup in the real world would be. So we extended our previous work, originally just designed for dual camera capture for the auto driving, into the generalized the multiple camera pipeline that simultaneously support monocular primary camera at a multi-view stereo array of the 19 synchronized cameras. And we tested if the number is increased, so the time delayed cannot be ignored. So, and this is the reason why we just limited our camera just in some the -45 to 45, and also only have the 3 elevation. So in our scenario, all cameras are moving, and adding the more cameras compounds latency. Just to handle this, we designed the custom plugin that semi-freeze the game graphic state while keeping the rendering and the physics engine active during the control the camera swap window. So with the careful scheduling, we reduce the per swap latency from the 16 millisecond down to the 0.2 millisecond. So making the depth ready and high resolution multi-view capture of the dynamic scenes possible. And here's what's the synchronized view looks like. And this table just compares the key attributes across the popular dataset for the dynamic 3D reconstruction. Just because for our we need to use the code map to do the pose estimation and to align all of the cameras in one space. However, for a lot of the multi-view cameras dataset only have the static camera setting. So if we only want to use the monocular camera, so it uh, cannot be cannot be work. Yes, otherwise we have to introduce the other cameras and information into the point cloud. So I think it's not unfair. So we have our own dataset. So this is a qualitative comparison. Just compared against other the metals, both the synthetic data and also the real data. This is on our data sets. So the null view rendering quality of our metal is clear structure, particularly in the maintaining the shape and color stability of the dynamic object. And also for the DyNeRF, render the dynamic and see the dynamic content with the reasonable clarity, but lost the geometric structure. So it's really like a cardboard, appeared flat and cover-like, and the background blur or something. And this is the Gaussian's work and the D3DGS to preserve the backgrounds sharpness. For some part is sharpness, but suffer from the inaccurate depth in the dynamic region. Just object fracturate and spilled apart whenever the view rotate. And this is only for the 30 degree. And this is rotating. The readout is on the first three is our SynDM dataset, the GTA 5 dataset, and this on the left, on the right two column is from the NVIDIA dynamic datasets. Good. And here's the table, and so it looks good. Just produce our method just produced the sharpest rendering and achieved the best PSNR. And here's quantitative comparison on the DyNeRF dataset as well. And for the DyNeRF dataset, I just mentioned because training requires the camera motion, but the DyNeRF cameras are stationary, so which means the Comac cannot estimate the pose from any single camera alone. So we work around this by selecting the frame from the central camera, the camera 0, the camera 4, 5, 6 as a synthetic monocular trajectory. So switching between the cameras to create the necessary camera motion. So the outer camera then serves as the held out ground truth. So this is not quite the purely no the mono view. So just like the alternative method, just so. And we also get a really good readout on all of them. And here's the ablation study. Just to you can see just if we as I talked before, just only the loss L, the SR loss only does not help because the underlying the feature are too weak for the SR network to refine meaningfully. So using only the the NOVA view, the color loss just reduce the blur, but introduce the white artifacts. because there's no shape constraint. Conversely, only the sigma, the density loss, just keep the shape intact, but lost the color fidelity. This is also some numbers, borrowing numbers. And here's some limitation, like just comparing the baseline and the expanding nerve visually and the quantitatively just reviews some as we visually have greatly outperformed other, but quantitatively maybe not just outperform other greatly, because just we can see in the red box it shows the region where the expanding nerve produced a sharp and detailed reconstruction, yet the PSNR may actually score lower. So the pixel-wise heat map just explains our sharper output introduce the localized high density errors, while the baseline blurry readout has a smoother transition and therefore lower the MSE. So despite the poor perspectual quality, so just because we um, align the thread prior from the Gaussian splatting and the uh, nerve space, it align these two space, it will have uh, some error. So you cannot just perfectly align these two. So it will be like also the line, the electric cable. And you can see it's looks clear, but actually it have the really high uh, the arrows in this region. Okay, I think this is all of my presentation.
All right, thank you very much. Yeah, there are some questions here in the Q&A. First question is, since SynDM is rendered
Yeah.
from GTA 5, does the method transfer to non-driving or non-real world scenes, or is it tuned to the simulator's visual statistics?
Mm. I think it's the pseudo for the first question is the SynDM is rendered from the GPU. Does the method transfer to non-driving? The non-driving real world sense. Uh, I don't think so. Just because the GTA 5 is not the camera is not totally fixed on the driving, just because we can set the cameras or everywhere just we want to set, just and put the humans or the animals in front of the dome we set, just like what we shows in the previous the slides. I'm not sure whether this is answered this question, but I'm a little bit.
No worries. We can go on to the next question here. The pseudo ground truth is doing a lot of work. How noisy is it? And does the model learn to trust it less where it's least reliable?
Mm, yeah, just the pseudo conscious is doing really a lot of the work. So the performance I think is quite based rely on the prior three Gaussians model we used. So, but actually, I think this pipeline is quite the agnostic of the all of the part. So when this uh the Gaussian splatting or the nerves or just keep keep developing, just we can switch to the stronger and robust the prior. So this is a can also improve the result.
Question here, does your method work on partially occluded objects?
The method. Oh, yeah, yeah. This is a really good question. Just because the this is what we want to test before, but the if it's the object is blocked, we need to just uh to build the the 3D prior from the occluded frames. However, just we don't know what is the true on the on the occluded side. So it's really hard just to so that part is totally being like the hallucinated. So uh, I think it's a really good direction just to to do the further research.
And last question we'll take here is where does ExpanDyNeRF actually break? Are there particular motions, articulated objects, or angles that are past some threshold that might cause ExpanDyNeRF to break?
Uh, wait. I still need to read
Oh,
that
yeah, yeah.
question. Yeah,
Here, I
I'm
accidentally
reading that.
dismissed it.
Yeah,
So here, reopen. There
yeah.
we go. Yeah.
Where does expand manufacturing take away? So, can I ask what's the breaks means? Just
I guess failure mode.
yeah, just yeah, actually, if the uh for some, I think just for some rapid moving object like the Uh, just we have tested some when some because in the GTA 5 it has the human or the animal it has some different types of the action. For some actions, if the action is really difficult and moving really fast, so we really hard just to capture to build the temporal consistency between the different frames because the basically use the thread prior to generate the thread prior for each frames. So if the between the two consecutive frames the difference is too large, so it's really hard just to build really like the temporal consistency in when we render or try to render the frame the two consecutive the frame.
All right.
Yeah,
Yeah, thank you very much, Lee. And just last question here. I've dropped a link here to the archive paper, but is there any project page or code or links to where people can find the data set or the model at all? Have those
yeah,
been made public? If so, can you
yeah.
just drop them into the chat for us?
Chat. Okay, okay. I'm gonna open the try to open that.